Okay, so in this video, I want to talk about the logistic function, which is this nasty looking thing. Um, and one of the things that I mentioned in class is we talk about exponential growth all the time in terms of like using it as a model for how populations expand and stuff like that. But if you think about it, no matter what kind of population you're talking about, it's not going to grow like an exponential forever because that's sort of ridiculous in reality. At some point, you run out of food or space or water or something like that. So, really, what happens is that it tends to taper off over time and you kind of reach this maximum sustainable population. And so that's where logistic models come in handy. And if you were to graph this sort of thing, where C, A, and K are all positive numbers, then you end up with a picture that looks more like this, where you kind of see that, okay, it grows quickly and then it starts to taper off at some point. So what we're going to do is, now that you know what the graph looks like, it'll help a little bit, but we'll analyze this algebraically instead. So let's see. Let's talk about if this was a population, if f of x was a population thing and x was time. One of the questions often is, what's the initial population? So that would be, what's f of 0? So if we plug in 0, we get c over 1 plus a e to the negative k times 0. And that turns into c over 1 plus a e to the 0. And e to the 0 is just 1. So this turns into c over 1 plus a. So I've got that. Okay. Another question that often comes up is, well, what happens way out at x equals infinity? So that would be, what happens as x goes to infinity? What's the limit of f of x as x goes to infinity? So we'll write limit as x goes to infinity. And then here we'll put c over 1 plus ae to the negative kx. Now, I'm not allowed to plug in infinity for that x right there. So instead, I'm going to do a little side work here. As x goes to infinity, think about what e to the negative kx does, right? E to the negative kx is the same thing as 1 over e to the kx. So if I were to, theoretically just think about plugging in some really big number, close, like a billion into there, then I've got 1 over e to some massive number, which is like 1 over infinity. So this thing gets really close to 0, which means this same version of it, written in a different way, also gets really close to 0. So then I can come back up here and say, okay, this turns into c over 1 plus a times 0, which is just c. So that tells me, knowing what our picture kind of is going to look like, that way out here at infinity, way out along this graph as x goes to infinity, I approach this value of c. So that means that y equals c is going to be a horizontal asymptote on the right side of this graph. It also, because of the way this function works, it turns out it's always below that horizontal asymptote. So y equals c, or let's say c, is also an upper bound for f of x. So we get two things out of that. Okay. So when you're doing a problem that talks about maximum sustainable population, something like that, well, plug in as x goes to infinity. One thing to be careful about, sometimes you run into a problem where it's not a 1 right here, it's a 2. So in that case, c would not be the maximum population. It'd be c over 2, or whatever number I just highlighted here, whatever number that would be. Okay. Then one other thing that often we look at is what happens as x goes to negative infinity. So if you go backwards in time. If you think about population growth, if you go backwards far enough, eventually you don't have anybody around. So it ought to be 0. So let's see if that actually happens. So c over 1 plus ae to the negative kx. And so again, I'm going to do a little side work here. So if I take e to the negative kx, and I say, well, let's let x go to negative infinity, then e to the negative kx, that's like saying e to the negative infinity, so e to the positive infinity. That explodes. That goes up to infinity. So then what you've got is c over 1 plus a times infinity, which is like c over a really big number. C over a really big number turns into 0. So that tells us, if we go back up to the picture, way out here, I've got a horizontal asymptote of y equals 0. So in my picture, or in my notes here, I'm going to say y equals 0 is a horizontal asymptote on the left. And 0 is a lower bound for f of x. And then one other thing that we figured out here, the initial value, that point right there, when x is 0, y is c over 1 plus a. It depends on whatever number is right there. If it's 2 on the bottom, then it'll be 2 plus a. Okay, hope that helps.